In 1981, the Swiss physicist Heinrich Rohrer and his colleague Gerd Binnig created the scanning tunneling microscope. And even though the device was very limited in what it could do, it inspired scientists and engineers to imagine what the world would be like if they could design and create everything around us at the atomic scale. If this was possible, we could create materials that vastly outperform those that we use today. We could develop super efficient ways of generating and using renewable energy, or computers that leave today's devices standing in the dust, or even radical new ways of treating and preventing disease. Amazingly, we're well on the way to achieving all of these and more. We've been becoming increasingly adept at manipulating materials down at the scale of individual atoms and molecules. We call these nanomaterials because we're working at such a small scale. In 2010, the Swiss National Science Foundation set out to try and understand how to fully realize the benefits of some of these fantastic new engineered nanomaterials that were coming along, while working out how to avoid any potential risks. Together they tell a story of how cutting-edge science and technology in Switzerland is realizing the benefits of engineered nanomaterials while helping to avoid unnecessary risks. This last century has seen incredible strides being made in how we treat disease, all the way from cancer and infectious diseases to non-communicable diseases like diabetes. But we've still got a long way to go in terms of improving our health and our well-being. Nanotechnology can help here by enabling diseases to be diagnosed earlier or delivering drugs to where they're most needed in the body. It can even help by replacing worn-out tissues like cartilage.
Cartilage is one of the few tissues that doesn't heal, it doesn't regenerate itself. So when it's damaged, surgery is often the only option. We use nanofibers in the polymer. We process these materials into a porous structure. And we use that porous structures to grow cartilage cells.
Artificial cartilage needs to be durable, but sometimes we need implants that do what they need to do and then disperse when their work is done. One exciting area of research here is the use of intentionally designed nanometer-sized particles, or nanoparticles, in materials that are designed to help reconnect blood vessels in the brain.
So in this case, nanoparticles are used. They are put in a patch around the vessel. Then we insert a laser in the blood vessel, and the laser light then solders the blood vessel by heating up the nanoparticles.
Nanomaterial-based implants are all about putting beneficial nanomaterials into our bodies. But we can also use nanotechnology to create materials that can take harmful stuff out of our bodies. One way we can do this is to make nanoscopically small particles that can mop up and remove toxic substances in our blood.
We have the blood outside of the body, and then we inject nanoparticles into the bloodstream. And these nanoparticles are covered with catching agents to catch proteins, to catch metals. And then we add a magnet to eliminate these harmful substances.
Nanoscale drugs are an especially exciting area of research at the moment. By taking really powerful medicines and forming them into nanoparticles, we can get them to precisely where they need to be in the body. But for them to be effective, they have to evade the body's defense systems.
There are different parameters which are important for the induction of an immune response. It's the material, it's the surface, and it's the size. So we have seen that nanoparticles in a size range of about 50 to 100 nanometers and with a specific surface can induce more prominent immune reactions than others.
Understanding how to ensure nanoscale drugs do what they're designed to do without causing problems highlights both the opportunities and the risks of using nanotechnology in our bodies. Of course, many of us won't be experiencing nanotechnology-based medical treatments on a day-to-day basis, but nanometer-sized particles can and do get into our bodies in other ways. For decades now, nanoparticles have been added to food. Titanium dioxide, for instance, helps manufacturers achieve vibrant colors in everything from candy to cake topping. And silicon dioxide nanoparticles are used to stop spices and other powders from clogging up. Because we've been exposed to nanoscale particles like this for such a long time without any apparent side effects, it's been assumed that they're safe. But researchers are beginning to explore how they interact with our bodies just in case.
We found in our studies that silicon dioxide nanoparticles are able to induce an inflammatory reactions in our test cells. We have to see now if these results that we obtained in the reaction tube has any relevance for the whole organism, like for animals like mice or rats, and also then for humans, of course.
Of course, to be harmful, nanoparticles not only need to be able to get into our bodies, they also need to get to places where they can cause serious damage. And one of those places that we probably don't want nanoparticles to get is the unborn child being carried by a pregnant woman.
It has been shown like 550 nanometer particles could pass the placental barrier, while particles larger than 240 nanometers did not. Simply knowing that transfer does not yet imply that there's a risk for the fetus, so for this, more studies need to be done.
But it's not just our health that we need to be concerned about when it comes to nanomaterials. There's also the environment. The environment we live in is no stranger to nanoparticles. Every time there's a fire or a volcano erupts or a new wave breaks, billions upon billions of nanoparticles are produced. Over millennia, we've evolved to deal with these particles. But what if intentionally designed nanoparticles can cause more harm than these naturally occurring ones? Vera Slavakova and her colleagues have been investigating what happens when environmental organisms are inadvertently exposed to engineered nanoparticles released into the environment, and especially when they're released into water systems.
We are interested in surface water. In particular, we are studying Lake of Geneva. Nanoparticles absorbs and absorbs by this organism, and if their concentration is high, they can become harmful for these organisms.
When it comes to the environment, one nanomaterial in particular has received a lot of attention over the past few years: silver nanoparticles.
Silver-scale nanoparticles are really interesting for industry but also for consumers because of their antimicrobial activity.
Well, the silver in its dissolved form is known to be very toxic, not only to bacteria but also to many other aquatic organisms.
We have discovered that the silver nanoparticles are very efficiently removed from the wastewater stream during the wastewater treatment. We're talking about removal efficiencies in the order of 95% and more.
Based on our results, we think for the aquatic environment there is no immediate harm, but I think we should still be very careful with the use of silver nanoparticles.
Of course, while understanding the possible impacts of nanosilver is important, we also need to know what other sorts of nanomaterials are potentially being released into the environment and where they'll go.
We cannot measure them yet analytically, so we have to use modeling instead. The release depends a lot on the type of product where the materials are used. For some there's a lot of release, for example titanium dioxide release from sunstream. For others there's very little release.
By understanding how nanomaterials are potentially released into the environment and where they go, or how nanomaterials in our bodies might cause harm, we can begin to build a picture of where future risks might lie. And this is essential if we want to ensure the full range of opportunities that this technology offers without creating unnecessary risks. Balancing the opportunities and the risks of engineered nanomaterials is really important, but it's not always easy. And sometimes through our research we discover that what looked like a good idea doesn't work as well as we thought it would. Here's Francis Schwartz on using copper nanoparticles to preserve wood.
It was assumed that the smaller the particle, the better the copper preservative can actually penetrate the wood. I found them to be comparable with conventional copper-based wood preservatives.
Findings like this might seem a bit disheartening, but they're especially important in helping make informed decisions on how nanotechnology is used most effectively and with the greatest benefits. And in other cases, this balanced approach shows how nanotechnology can be used effectively and safely. Take the use of carbon nanotubes to make strong materials, for instance.
Carbon nanotubes have exceptional properties such as high strength and stiffness. If they are put into the polymer matrix, they could form an interconnected network, thus giving rise to stronger structural toughness, flexural modulus, and increased electrical conductivity.
Unfortunately, if these long, thin nanotubes become airborne and are inhaled, they can cause considerable lung damage. And so to be used successfully, it's important to make sure that they stay where they're supposed to.
We used aging experiments and immersed these composites into water, exposed them to UV light. In these experiments, we did not observe a release. However, in abrasion experiments, we did observe release.
In the case of carbon nanotube composite materials, there are clear opportunities with using nanotechnology. And while there are important concerns about possible health risks, we discovered that because release and exposure are likely to be very small, the benefits far outweigh what look like negligible risks. This ability to re-engineer common materials and to use them in new ways is a common theme in nanotechnology. Another example is how we can use natural materials in new and interesting ways, like cellulose, for instance.
Cellulose is the most important structural component of all plants. It's actually quite simple to disintegrate wood and isolate the individual nanofibers. They are super stiff and super strong and are therefore of interest to make composites. So when we started out, the idea was that nanocellulose is safer than engineered nanoparticles because it's a biological material. But at that time, there were no studies available that really supported that hypothesis. In the meantime, we and many others have done experiments that confirm that if used in realistic doses, nanocellulose is much safer than other materials.
Another area that has been attracting a lot of attention is using nanomaterials to increase the performance of lithium-ion batteries.
Nanomaterials in battery have already proven that it can increase the power available from a battery, and second point is decreasing the time required to recharge a battery. So we have big enhancements in capacity and energy in weight and in volume, and also we could recharge our batteries in shorter time compared to micron size.
Engineered nanomaterials are without a doubt an incredibly powerful technology. They can transform our lives and our livelihoods, but as we've seen, they're not always risk-free. The challenge we face is how to take advantage of this technology to improve lives, protect the environment, and support economic growth without causing unnecessary harm. This is the challenge that the NRP 64 program set out to address. Through the 23 projects that it supported, considerable strides have been made in how to use nanomaterials to benefit lives and create economic opportunities while avoiding potential risks. Over the past few years, these projects have just scratched the surface of what's possible using engineered nanomaterials. But they've shown us what we can achieve if we use science and evidence to understand both the opportunities of these technologies and the risks that they present. And perhaps most importantly, they've moved us closer to being able to develop and use engineered nanomaterials in ways that create jobs, improve our lives, and help cure disease, all without causing more problems than they solve.